You know that feeling? You're just swamped with information, and all you want are the key takeaways, the really important stuff, without getting totally lost.
Yeah, absolutely. Information overload is real.
Well, that's exactly what we do here. Welcome to the Deep Dive. We're your shortcut to, well, getting informed. Today, we're diving into dynamics and agent systems in design, just for you.
And this is a really fascinating space. It builds nicely on design stuff you might already know, things like geometry, maybe data structures, algorithms.
Right.
But now we're looking at how adding time, interaction, and even, individual behaviors can really shake up how we think about design.
Exactly. So our mission here, using materials straight from a data and design class, is basically to pull out the core ideas of these dynamic approaches.
Hmm.
We want to understand how letting systems change over time, how individual bits interact, can create design results that, well, static methods just can't touch. Moving beyond the fixed into the fluid, you could say.
And we've been looking at excerpts from lecture videos covering this, so we're trying to bring that classroom insight directly to you.
So what we hope you'll get by the end is a pretty solid grip on key things like spring models, particle systems, those really cool flocking algorithms,
Right.
and figure out why they matter for design thinking without, getting bogged down in super technical jargon. Okay, let's dig in. What exactly is dynamics when we talk design?
Okay, so dynamics in design, essentially, it refers to approaches where the state of the whole system changes over time.
Okay.
It's about setting up designs where the final thing isn't just static, defined by one set of rules, but it's the result of uh, a sequence of steps, calculations, interactions unfolding. You're basically designing a behavior, not just a final shape.
So like instead of drawing a line and that's it in a dynamic system, that line could maybe ripple or bend based on other things nearby, or even react to, I don't know, forces over multiple steps.
Exactly, yeah.
Yeah.
And the lecturers pointed out we can create these kinds of evolving designs using different tools. They mentioned things like vector fields.
Vector fields, right?
Think of those as like directional forces across a space. Also, agent or particle systems, spring models where elements are connected by, well, virtual springs, and even simulating how rigid bodies interact. All these let us bring movement and change right into the design process itself.
All right, that gives a good sense of dynamics. Now, what about agent systems? What's the main idea there?
Agent systems really zoom in on the individual parts within a design. We call them agents. And the key thing is each agent can have its own parameters, its own rules for how it behaves.
Okay.
They're not just passive pieces. They can sense things, they can interact with each other and with their environment too.
Ah, so it's like going from one big set of rules for everything to lots of individuals, each with its own little program, kind of influencing each other back and forth.
Precisely. And this is where it gets really neat. Even if you have tons of very simple agents, right, each following pretty basic rules, their combined actions, their interactions, can lead to incredibly complex, often surprising, overall patterns in the design.
Wow.
The final result isn't something you explicitly told each agent to do. It just sort of emerges from them, all interacting together over time.
And this doesn't mean we throw out other methods like parametric design or generative stuff, right? How do these dynamic things fit in?
Oh, not at all. No, dynamics and agent systems aren't replacements. Think of them more as powerful additions to your design toolkit.
Right.
You can absolutely use them with parametric design where you define relationships, or with generative methods that explore lots of options. It's really about having more tools in the box and picking the right ones for whatever design problem you're tackling.
That makes sense. Expanding the options. Now, the lectures got into specifics. Spring models came up. What's the basic idea there?
Spring models are a really intuitive way to grasp dynamic relationships. Imagine you've got a bunch of points, nodes, right?
Right.
And they're connected by invisible springs.
Okay. Virtual spring.
Yeah, virtual springs.
Right.
And each spring has a sort of natural length it wants to be. If the distance between two connected points gets shorter or longer than that ideal length, the spring basically pushes or pulls to try and get back to it.
So if 2 points get too close, the spring pushes them apart. Too far, it pulls them together.
Exactly. And the speaker in the lecture had a really good way of explaining it. They said, imagine the target length is, say, 1 unit. If the actual distance is less than 1, you apply a little force to nudge them apart. If it's more than 1, a little force to pull them closer. And you just keep doing that calculation, that adjustment, over and over. It's an iterative process. Eventually, the whole system kind of settles into a balanced state and equilibrium. That's the core of a spring model.
And the lecture showed some really cool applications like circle packing. How does that connect to spring models?
Well, we usually think of packing circles neatly, like on a grid, right?
Yeah, very ordered.
But using a dynamic spring model lets you get a more, well, organic arrangement. You can treat each circle like a node that basically pushes away its neighbors if they get too close,
Oh.
like a repulsive spring with a really short target length. So as these circles jostle around, pushing each other, they find a way to pack together tightly, but it often looks much more natural than a strict grid. The lecture showed some really nice 2D and 3D examples.
They also mentioned using them for tensile structures and interactive point grids. How do springs work there?
For tensile structures, you can imagine the cables or the fabric pieces
Hmm.
as the springs. You set their target lengths, let the system run through those iterative adjustments, balancing the forces, and boom, you simulate the final tension shape.
Okay, I see.
And for interactive grids, picture a grid of points, all linked by these springs. If you grab one point and move it, the springs pull on its neighbors, they pull on their neighbors, and you get this smooth, kind of elastic stretching across the grid. The demo even showed pulling one point, causing this ripple effect through the whole thing. It's all driven by those spring connections trying to reach their target lengths. Very intuitive for creating responsive shapes.
Okay, springs make sense for relationships. Let's switch gears to particle systems. This sounds more like simulating actual physics, movement, forces.
That's exactly it. Particle systems are about individual elements, particles, and how forces make them move. The lecture brought up Newton's second law, ESMA, force equals mass times acceleration.
Right.
The speaker might have mentioned velocity briefly, but the crucial thing is that forces cause a change in velocity. That's acceleration.
So with springs, it was mostly about position and forces based on distance. Now, particle systems are explicitly about how forces change motion speed and direction.
Exactly. For every particle, you're typically tracking its position, the forces acting on it, and its current velocity. Then, in each little time step of the simulation, you calculate how those forces cause acceleration, and you update the velocity and then the position.
Okay.
And the lecture showed off a few basic force types. There was gravity, obviously, pulling things down.
Hmm.
Attractors, which could pull particles toward the point or even push them away. And external forces, like literally grabbing and moving particles with the mouse cursor.
And the movement patterns looked really different depending on the forces, didn't they?
Oh, absolutely. We saw particles just cruising at a constant velocity if no force was acting. Give them an initial push and impulse, and they'd go in a straight line, maybe slowing down due to simulated friction, or damping.
Right, damping.
If you had attraction towards a point, plus the particle's own momentum, you got those nice curved sort of orbital paths.
Yep.
Interestingly, if the attraction just forced a constant speed, they moved more directly towards the attractor point. And gravity, of course, gave those classic parabolic arcs.
Uh-huh.
The lecture also quickly mentioned adding collision detection, so particles could bounce off things realistically. Adds another whole layer to the simulation.
Okay, got it, for individual particles. Now, what about when lots of these particles interact as agents? That brings us to flocking or Boids. That stuff always looks amazing.
Yeah, the flocking algorithm is just a brilliant example of complex, coordinated group behavior emerging from really simple individual rules.
Okay.
So the lecture explained that each agent, or Boid, basically follows three main urges. First, separation. Try not to crash into your immediate neighbors. Keep a little distance.
Has.
Second, alignment. Try to steer in roughly the same average direction as your neighbors. Go with the flow.
Okay.
And third, cohesion. Try to move towards the average position, the center of your local group. Stick together.
So don't collide, match direction, stay near the group. That's it.
That's basically it. And the speaker used a great analogy, film frame rates. Like a movie is just fast, still frames. Flocking works by updating each Boid's position and direction based on these rules many times a second. It's that constant tiny adjustment by every agent reacting to its neighbors that creates those incredibly fluid, organic-looking flock movements.
Wow.
The overall flock behavior isn't programmed in, it just happens from all those local interactions.
And it's worth remembering, like the lecture said, this isn't necessarily how birds actually fly in minute detail, right? It's more a simulation capturing the look of coordinated movement.
That's a really key point. It's a compelling simulation based on observation. And what makes it super useful for design is you can tweak it. There are parameters.
Ah, okay.
You can adjust things like the maximum force a Boid can use, how close it looks for neighbors to avoid, how strongly it tries to align, how much it cares about staying with the group center. The demo even showed the whole flock dynamically following the mouse cursor around. Shows how an external influence can guide the emergent behavior.
So these agents, they're not just floating in space. They're usually in some kind of environment that affects them. The lecture mentioned vector fields for this. What are those?
Right. A vector field is basically a way to define and influence a direction and a strength at every single point in a space, like an invisible map of little arrows pushing things around.
Okay, like wind, maybe.
Yeah, or currents. Agents in that field can then sense the vector right where they are and react. So a particle might just move in the direction of the vector at its location, maybe faster if the vector is stronger.
And you can visualize these fields by dropping particles in and watching where they go, creating those flow lines.
Exactly. You trace the paths of lots of particles responding to the field, and that visually reveals the underlying structure of forces and directions. The lecture even mentioned a cool Berkeley project, using probability fields and velocity fields, areas where things move faster or slower, to guide particles moving across a map. Shows how you can use real data to create these influencing environments for your agents.
With all this interaction and feedback, it feels like there could be a lot of unpredictability. The lecture talked about the stochastic nature of agent systems. What does that mean for design?
Well, some computational methods are deterministic, right? Same input, same output every time.
Yeah.
But agent systems often have randomness, stochasticity baked in. Maybe the starting positions are random, or there are slight variations in how agents react, or random forces get introduced.
Okay.
This randomness means the outcomes aren't totally predictable, but that can actually be a good thing. It can lead to designs that are richer, more varied, maybe more surprising and innovative than purely deterministic methods would produce. You might stumble onto really valuable solutions because of that element of chance.
This all sounds incredible, powerful, but maybe also potentially very complex to manage. The lecture really hammered home the importance of object-oriented programming, OOP.
Why is OOP so vital here?
Oh, absolutely vital. OP gives you the structure you need to handle the complexity. I mean, think about it. You could have hundreds, thousands of these individual agents.
Each one has its own data position, velocity, maybe internal states, and its own behaviors, how it moves, interacts.
Mm-hmm.
OOP lets you organize this chaos. You define a class, like a blueprint for an agent.
The blueprint, okay.
And then you create individual objects, actual agents, from that blueprint. Concepts like encapsulation, keeping an agent's data and its actions bundled together, modularity, breaking the system into manageable chunks, and hierarchies defining relationships between different agent types. These become essential for keeping the code organized, understandable, and fixable as things get more complex.
The speaker was very direct. They said you absolutely need to know OOP to handle the data in these simulations. Really underlines it.
It really does.
Yeah.
The lecture used a building analogy. A room has walls, walls have doors, windows. That's a hierarchy. But with agents and OOP, relationships can be smarter, more context-aware. Like a wall object might decide what kind of window objects it needs based on its orientation or what's happening nearby.
Ah, more dynamic relationship?
Yeah. And that lender-borrower remembers a loan example showed how OOP choices reflect different ways to manage agent states and interactions. Design patterns were also mentioned, basically. Reusable templates for solving common coding problems in OOP, very helpful in these contexts.
It sounds like having a really good organizational system for building something complex with lots of moving parts. Now, the lectures didn't just stay theoretical. They showed real-world applications. Can you remind us of some of those examples?
Sure. We saw the basic ones, again, like circle packing, using those repulsive springs, simulating tensile structures, also basic particle physics like bouncing and, of course, the flocking behavior.
Right.
But then more advanced stuff, too, like arranging overlapping pop-up windows on a map so they don't hide each other using an iterative dynamic fitting process.
Oh, yeah, I remember that one.
Another was simulating structural support in a design. Individual elements acting as agents would adjust themselves to try and maximize overall support, dealing with constraints, maybe even using randomness to find new structural forms.
Yeah.
And there was even an example modeling a simple ecosystem agents representing trees, water, ground, interacting, exchanging resources based on rules in the environment. Shows how you can use this to simulate and maybe design complex systems like that.
Those examples really show the range, don't they? From pure aesthetics to complex functional simulation. It also sounds like a big part of this is just trying things out, simulating, tweaking, simulating again.
Absolutely. It is fundamentally an iterative design process. You're constantly fiddling with the knobs, right? Adjusting damping, force strengths, target lengths for springs, separation distances for flocking.
Yeah.
Tweaking all those parameters to steer the simulation toward the kind of behavior or result you want. It's a cycle.
Yeah.
Simulate, observe, refine, repeat.
The lecture was crystal clear.
Mm.
To really get this, you have to code. The speaker had that great quote.
Oh, yeah, very emphatic. Don't learn swimming by reading. Get in the water. Yes. In the end, it's coding.
Cup.
It really drives home that, theory is one thing, but the real understanding, the deep intuition, comes from actually writing the code, running the simulations, seeing it work or not work yourself. You can read about flocking, but implementing it, that's when you really understand how those simple rules interact.
It's like any craft, right? Learn by doing. Now, the lecture also touched briefly on bigger picture stuff, challenges, the future of computational design.
Yeah, a couple of interesting observations. One was the sort of uneven adoption across industries. The speaker noted fields like, surprisingly, agriculture sometimes adopting these methods faster than, say, architecture.
Huh, interesting.
And also that big changes in computational design often seem driven by external things like big data becoming available or progress in AI rather than just internal developments within design itself. Those outside forces create new needs and possibilities for these techniques.
And wrapping up, the lecture directly encouraged you, the listener, to think about how dynamics and agent systems could apply to your own work, your own interests.
Exactly. The challenge was, could you frame your problems as simulations? Could you think of the parts as interacting agents? What forces, what behaviors define them? How does their environment shape things? And what kind of unexpected emergent outcomes might you discover if you looked at it that way?
So, to sum up this deep dive, dynamics and agent systems offer these really powerful new ways to tackle design. They bring in time, interaction, individual behaviors. They build on programming fundamentals, especially OOP. And they open doors to simulating complex systems and finding innovative solutions that go way beyond static forms.
And maybe a final thought for you to chew on. Think about some system you interact with daily. Could be a city, social network, traffic, anything. How might you start to model that using these ideas of dynamics and agents? What new perspectives or design ideas might just pop out from looking at it that way?
We definitely encourage you to dig deeper into some examples or maybe even, dip your toes into some basic coding with springs or particles. It really is the best way to make these concepts stick and see the potential firsthand.
Yeah, because ultimately understanding these computational approaches is becoming more and more valuable. We live in a world driven by data, by complex interconnected systems. This gives you new ways to think about that world and maybe even new ways to help shape it. It really opens up some exciting paths for the future of design.